Imagine you're controlling a remote control car.
Okay.
You steer, it moves. And if it hits a wall, it just spins its wheels helplessly
Right.
until you manually walk over and back it up.
Yeah, you have to physically intervene.
Exactly. And that is essentially how we've interacted with artificial intelligence up to this point. But what if, instead of an RC car, you were operating a Mars rover?
Oh, that's a very different paradigm.
Right. You don't steer it. You just give it this high-level command like, go analyze that rock formation.
And it handles the rest.
Yeah. If it encounters a crater along the way, it doesn't just call home for help. It mathematically calculates its own path, it navigates around the danger, and completes the mission completely autonomously.
Which is incredible.
It is. And, well, welcome to this deep dive. Because today we have a fascinating stack of sources anchored by this really comprehensive seminar technical report from the Technical University of Munich.
A really solid paper.
Yeah, the topic, the fundamentals of building autonomous LLM agents.
Which, it's a massive structural leap in computer science right now.
Oh, for sure.
Engaging with these LLM agents, it's really like engaging with a new species of digital collaborator.
A new species. I like that.
Yeah, because we're moving away from language models that just passively generate text in a chat window.
Right. Standard chatbot.
Exactly. And we're moving toward autonomous systems that are actually built to execute complex multi-step actions in, dynamic, really unpredictable software environments.
Okay, let's unpack this, because before we can understand how we actually structure the digital minds of these agents, we kind of have to separate true autonomous agents from, well, the basic automations you might already be running in your own tech stack.
Yes.
Like there's a fundamental difference between a workflow and an agent.
A huge difference.
But I have to ask, if I take a standard large language model, an LLM, and I hook it up to a calculator tool or like a web search API, doesn't that make it an agent? It's using tools to do a job.
So that is actually the most common misconception in the space right now.
Oh, really?
Yeah. Simply equipping a model with tools does not make it an agent. It makes it a workflow.
A workflow, okay.
Right. A workflow is a rigid pipeline. It relies entirely on a preset human-designed sequence of events.
Like the RC car.
Exactly. Think of your RC car on a very specific pre-built track. It runs super efficiently as long as the track is perfectly clear.
But if something goes wrong,
like an API times out or a website changes its layout, the workflow just crashes.
right, it just spins its wheels.
Yeah, it has absolutely no internal mechanism to recover. But an agent, like your Mars rover, possesses dynamic autonomy.
So the defining factor isn't the tool itself.
No, not at all.
It's the internal feedback loop. Like if an agent tries an action and fails, it reads that failure state from the environment, rewrites its own strategy on the fly, and just tries a completely different route.
That is the core distinction, yeah.
Right.
And if we connect this to the bigger picture, for an AI to actually possess that kind of dynamic, self-correcting autonomy, it requires a completely different architectural foundation than a standard chatbot.
Which the Munich researchers break down for us.
They do. They outline 4 core cognitive systems that have to operate in tandem.
And those are?
Perception, reasoning, memory, and execution.
Okay, well, let's start with the first one, perception.
The eyes and ears.
Right, because if this digital Mars rover is going to navigate a desktop environment, it actually needs to, well, see the screen.
It has to know what it's looking at.
Yeah, and the research focuses heavily on multimodal large language models.
MM-LLMs.
Right, which process both text tokens and visual data, like screenshots.
Yeah.
But looking at an image and actually understanding a user interface are 2 very different things.
Entirely different.
And the sources detail this specific upgrade called set of mark, or SOM.
Yeah, set of mark is this fascinating engineering solution to a major visual limitation with these models.
Because they can't see perfectly.
Well, standard vision models struggle with spatial precision. Like, they can tell you there is a submit button somewhere in the image,
Okay.
but they can't easily pinpoint its exact pixel coordinate.
Which you need if you're going to click it.
Exactly. So set of mark uses a specialized visual encoder to physically draw bounding boxes around every single interactive element on a graphical user interface.
Oh, wow. So it essentially annotates the screen like a football coach drawing plays on a chalkboard.
Yes. That's a great way to picture it.
Yeah.
And crucially, it assigns specific Cartesian coordinates, an X and Y value, to every single one of those boxes.
So he knows exactly where everything is mathematically.
Right. But visual data alone isn't enough.
It's not.
No, the agent actually layers that visual grid with structural data. It pulls what's called the accessibility tree, or A11Y tree.
Okay, what's that?
It's the hierarchical data structure generated by your operating system, and it pulls that alongside the raw HTML code of the web page.
Oh, I see. So it's cross-referencing. It looks at the visual layout to see where the box is, but it reads the underlying HTML to get the semantic grounding.
Yes, to prove mathematically that this specific gray rectangle functions as a drop-down menu.
Right, right. But here is where the real world gets messy.
Always does.
What happens when a random pop-up ad suddenly appears? Or, one of those massive cookie consent banners shifts the entire window layout while the AI is right in the middle of trying to calculate those coordinates.
Yeah, so that introduces what the researchers call unexpected window noise.
Window noise.
Right, and it is a massive hurdle because when the layout shifts unpredictably, that coordinate mapping we just talked about, it completely breaks down.
Bounding boxes are all in the wrong place now.
Exactly. Furthermore, processing those high-resolution images alongside complex HTML trees, it creates severe latency bottlenecks.
It slows the whole system down.
It crawls. And most concerningly, agents suffer from visual hallucinations.
Wait, visual hallucinations?
Yeah, the model will confidently see and attempt to interact with buttons that simply do not exist in the visual matrix.
Oh, man. I mean, if you've handed an AI the keys to your financial software or like your live database, a visual hallucination could be disastrous.
Yeah. So how do they actually mitigate that?
Well, the report highlights a tool called vCoder.
Okay.
Rather than just feeding the model standard RGB pixel data, like a normal screenshot, vCoder feeds the perception system specific segmentation masks and depth maps.
Depth maps. So it's not just a flat image anymore.
Right.
It's providing like a matrix of depth values. So the model inherently understands the difference between a background element and a foreground pop-up.
Precisely. It gives the model a much finer-grained mathematical understanding of the spatial relationships on the screen.
That's brilliant.
It helps a lot.
But even with depth maps, perception is an evolving challenge. And the perception system has to be as accurate as possible because whatever it sees
flows immediately into the next architectural pillar.
Yes, the reasoning system, the brain.
Right, because once it maps that visual matrix, it has to decide its next move. And the core of this system is task decomposition. Right.
Taking a massive abstract goal and breaking it down into executable subtasks.
Right. And the research outlines a pretty stark evolution in how models handle this.
Yeah, historically, models used what we call interleaved planning methods.
Like chain of thought.
Chain of thought or REACT. In an interleaved system, the agent processes sequentially.
Step by step.
Right. It takes one step, analyzes the result, plans the next step, takes it, and so on.
Which, I mean, that sounds logical.
It does.
But the paper points out a fatal flaw when it comes to really long tasks.
Yes, context loss.
Right. If you process strictly sequentially, the agent tends to lose track of the overarching goal.
It forgets what it's doing.
It's like going to the grocery store for milk, getting distracted by the bakery aisle and ending up with 3 types of artisanal bread while completely forgetting the milk.
That is exactly what happens. To solve that cascade of errors, developers engineered something called DPPM.
Which stands for?
Decompose, plan in parallel, and merge.
Okay, so how does that work?
Well, instead of a linear sequence, DPPM maps the main task into isolated subtasks. It then uses the LLM to generate independent plans for all those subtasks simultaneously.
At the same time.
Right. By isolating the context of each subtask, an error in step 2 doesn't inherently corrupt step 5.
It's quarantined.
Exactly. And finally, it merges those parallel plans into one coherent global strategy using a dependency graph.
Now here's where it gets really interesting. Because the paper discusses a specific framework for evaluating the quality of those plans.
Oh, the devil's advocate framework.
Yes, it introduces this concept called anticipatory reflection.
Which is brilliant.
It is.
Yeah.
The way I picture this, it's like the AI is playing chess against itself.
That's a perfect analogy.
Like before it even commits to a move, it explicitly tries to predict exactly how its own plan is going to fail.
Right. It's an internal adversarial process, and this reflection mechanism is what truly separates an agent from a workflow.
So how is devil's advocate actually structured?
It has 3 internal components. First, you have the actor, that's the module that generates the proposed action.
Okay.
Second, the evaluator. And third, the self-reflection model.
But wait, how does an LLM actually evaluate itself? I mean, is it just guessing if a plan looks good?
No, no. The evaluator relies on a strict mathematical reward function.
Okay, so it's quantifiable.
Yes. Let's say the actor attempts to click a specific download link. The evaluator looks at the resulting state of the screen. Perhaps it checks the new URL or the new visual layout
Right.
and compares it against the desired goal state. If the match score is low, meaning the action failed, that failure signal goes directly to the self-reflection model.
Oh, I see. So the self-reflection model analyzes the trajectory and realizes, like, oh, I missed the link because my spatial coordinates were off by 10 pixels.
Exactly.
And then it rewrites the prompt internally, updates the coordinates, and the actor tries again.
It creates a closed loop of learning.
Without any human intervention.
Zero human intervention. It isolates the variable that caused the failure and adjusts.
That is wild.
Hmm?
But think about the sheer computational weight of what we just described.
It's massive.
Right. If a single AI model is trying to process depth map matrices and parallelize multiple subplans and mathematically evaluate its own failures and rewrite its own prompts.
All at once.
Yeah. Wouldn't a single model just buckle under that cognitive load?
It absolutely does, which
Yeah.
is exactly why the architecture evolved into the third core system, multi-agent systems.
Splitting the workload.
Precisely. When the reasoning becomes too complex, you don't just use a bigger model, you divide the labor.
Okay.
A single agent interface is actually comprised of multiple highly specialized subagents working together in a coordinated environment.
It's essentially a trench coat filled with highly specialized AI experts.
Exactly.
You're creating like a virtual board of directors inside the runtime environment.
That's exactly what it is. And the research outlines specific roles for these directors.
Like what?
Well, you might have a dedicated planning expert whose sole architecture is optimized for strategic task decomposition.
Okay, the big picture guy.
Right. Then you have an error handling expert, a coding expert that's fine-tuned strictly on Python datasets to write execution scripts,
Wow.
and even a memory management expert. They're all built through highly targeted prompting and fine-tuning, and they communicate with each other through a shared context window.
I have to push back on this, though.
Sure.
If you introduce, say, a constraint expert that is constantly arguing with an execution expert about what actions are allowed based on security protocols, does that actually make the system better? Or are we just inventing, like, artificial bureaucracy that slows the whole thing down?
Well, it definitely increases processing time, but it's not about speed. It is entirely about robustness.
Robustness.
Right. The research identifies a massive failure mode in single-agent architectures, which is the repetitive loop. Yeah. A single agent will try an action, fail, and due to context limitations, it will just try the exact same failing action again, infinitely.
It gets stubborn.
Exactly. It just bangs its head against the wall. Modularity solves this.
Oh.
When the execution expert gets stuck in a loop, the error handling expert acts as an asynchronous interrupt.
That just steps in.
It recognizes the pattern of failure, overrides the execution expert's permissions, and forces the planning expert to generate a completely novel strategy. It prevents total system failure.
But hold on.
Yeah.
For that error handling expert to recognize a pattern of failure, it has to actually know what the execution expert just tried 30 seconds ago.
Right.
How does an LLM, which is by definition a stateless, memoryless text predictor, actually hold on to that context?
And that requires the next architectural pillar, the memory system.
Okay, because without it, the board of directors has amnesia.
Total amnesia. So memory is bifurcated into short-term and long-term structures.
Okay, let's break those down.
Short-term memory is basically the agent's context window. It's the immediate active RAM where it holds the current visual matrices and the active dialogue between all those subagents.
Right. And long-term memory is where it stores knowledge that persists across entirely different tasks.
Yes.
And the sources detail a few methods for this, right?
Right.
Like there is RAG, Retrieval-Augmented Generation,
Very common.
where the agent converts documents into vector embeddings
Right.
and fetches them when needed.
Right.
Then there are standard SQL databases for pulling structured data. And there is embodied memory, which I found fascinating. It actually bakes new procedural knowledge directly into the AI model's weights through continuous fine-tuning.
Yes, and there is also a highly specialized structure called Agent Workflow Memory, or AWM.
What does that do?
This is where the agent stores the exact step-by-step trajectories of successful tasks it has completed in the past.
Oh, like a playbook.
Exactly. If it encounters a similar goal, it doesn't need to reason from scratch. It just retrieves the AWM trajectory and executes the proven routine.
But there is a glaring mechanical issue with the short-term memory, isn't there?
The context window limit.
Yes, the context window limit. If the AI is meticulously tracking every single X and Y coordinate, every bounding box, every failed reflection, and every line of code written by its internal experts,
It fills up fast.
won't that context window just fill up instantly? Like it hits the token limit and the whole system crashes.
It is a hard mathematical wall.
So what do?
To prevent a crash, developers implement an active memory duplication management system.
Okay.
The research details this really brilliant condensation method. Let's say an agent completes 5 sequential, highly granular actions to achieve a single sub-goal, like navigating through 5 nested folders just to find a specific file.
Okay, so click, 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 right?
Right. Instead of keeping the token-heavy data for all 5 individual clicks cluttering up the context window,
Right.
the memory management expert uses the LLM to summarize those 5 sequences into one unified semantic plan. It consolidates the knowledge and deletes the redundant trajectory data, freeing up token space.
Wait, but if it's summarizing 5 actions into a single semantic sentence just to save memory, doesn't it lose the granular pixel coordinate data it might need if it has to navigate backward?
Yes.
Isn't that a dangerous, lossy compression?
It is absolutely a lossy compression, and that is a calculated trade-off.
Okay.
It discards the raw Cartesian coordinates but retains the semantic action. It understands that it navigated to the financial folder.
I see.
It trades immediate visual precision to maintain the overarching contextual awareness it needs to actually finish the task.
That makes sense. All right, so let's look at the whole pipeline. The agent has perceived the messy visual environment with depth maps.
Check.
It has used its team of internal experts to parallelize a plan.
Check.
It has checked its memory to avoid repetitive loops. Now, it actually has to do the work,
Yes.
which brings us to the final pillar, the execution system.
This is the translation layer. It's where abstract digital reasoning becomes concrete environmental change. The agent must physically interact with the system.
And it does this through 3 primary channels, right?
Yeah.
It can use API integrations to quietly manipulate data on the backend.
Which is standard.
Right.
Yeah.
Second, it can use dynamic code generation. Like, it spontaneously writes and executes a Python script to sort a massive database because it realizes that's way faster than manually clicking.
Much faster.
And third, it uses GUI automation, where it physically takes control of the mouse and keyboard, mapping its decisions to screen coordinates and clicking.
Right. These multimodal action spaces allow the agent to operate software natively, exactly as a human user would, entirely bypassing the need for dedicated developer APIs.
Okay, so we've outlined this incredibly sophisticated, multi-layered cognitive architecture. It sounds flawless.
On paper, yeah.
On paper, but the source material provides a massive, sobering reality check.
It really does.
The research references a major benchmark called OSWorld, which tests how well these agents actually perform real, complex computer tasks.
Right.
And as of the data in the report, this is around June 2025, humans complete these tasks successfully, 72.36% of the time.
Okay.
The absolute best, state-of-the-art autonomous models, they are stuck at about 42.9%.
Yeah. And this raises an important question.
Why?
Right. If the internal reasoning architecture features depth maps, and anticipatory reflection, and a whole board of specialized experts, why is there a nearly 30-point gap between human and AI performance?
Well, if the brain knows exactly what it wants to do, the breakdown must be happening in the translation to the hands, right?
Precisely. The perception to execution pipeline is deeply brittle. The researchers identified GUI misgrounding as a primary culprit here.
Meaning what?
The agent struggles to consistently map its visual bounding boxes to the pixel-perfect coordinates required by the operating system to actually register a click.
Ah, so it understands it needs to click submit, but its mouse cursor lands like 2 pixels outside the hitbox.
Yes, it misses the button. Furthermore, agents lack deep operational knowledge.
What do you mean by operational knowledge?
Well, a human inherently understands the unwritten rules of digital physics.
Digital physics.
Yeah. If a web page isn't loading, a human knows to refresh or scroll down or maybe check the Wi-Fi connection.
It's intuitive.
But an agent does not have a lifetime of embodied common sense interacting with computers.
Yeah.
Even with an error handling expert, if it encounters a novel edge case that it hasn't been explicitly trained on, the architecture really struggles to improvise.
So they are incredibly intelligent, but they completely lack screen smarts.
Exactly. Training these models on the infinite, chaotic edge cases of human-computer interaction is exceptionally complex. The reasoning is sound, but the physical embodiment of that reasoning is still very shallow.
Wow. But looking at the big picture, the leap we're making is still staggering.
Oh, absolutely.
We're moving from simple text predictors to four-part cognitive architectures: perception, reasoning, memory, and execution.
It's huge.
We are building systems capable of externalizing human reasoning, creating a digital collaborator that can navigate really messy environments.
It is a fundamental reshaping of how work will be accomplished. We are just scratching the surface of what these autonomous pipelines can execute.
Which brings us to a final, incredibly provocative thought from the research.
Yeah, this part blew my mind.
Right. Because right now, the standard paradigm is that humans supervise the AI. You give the agent a goal, and you watch it work, stepping in when it fails.
Right, you're the boss.
Exactly. But the paper hints at future research directions that flip that dynamic completely upside down. They suggest that to achieve a 10x improvement in global productivity, we might need to develop systems where humans act as the assistants to the AI agent.
It's wild.
Think about that for a second. You log into your workstation tomorrow, and an autonomous LLM agent, which has already analyzed the company's global data, planned the quarterly strategy, and decomposed the massive goals into parallel subtasks.
It just assigns you a task.
Yes. It assigns you a specialized task, simply because you have the physical hands or the specific nuance required to finish its global strategy. The digital encyclopedia didn't just grow legs and do the work.
Yeah.
The intern just became your boss. Something to mull over the next time you ask an AI to summarize a PDF for you. Thank you so much for joining us on this deep dive. Until next time.